Hi, this is Shunsuke Aoki, an assistant professor at National Institute of Informatics at Japan, and this work is with Carnegie Mellon University and General Motors in the US. The talk title is MultiCruise, Eco-Lane Selection Strategy with Eco-Cruise Control for Connected and Automated Vehicles, and we discuss an energy-efficient lane selection strategies for self-driving vehicles. This talk is recorded for IEEE Intelligent Vehicles Conference 2021. First of all, fuel efficiency is a very important topic for vehicles. According to the US government, over 150 billion gallons have been consumed per year in the US alone. Also, motor gasoline and diesel fuel is the biggest CO2 source in the US. To save the energy consumption, each vehicle has to maintain the optimal speed, which depends on the vehicle types. In fact, motor companies have vehicle fuel table for each vehicle types, which is presented in the right figure. By using the given speed and acceleration, we can know the expected fuel consumption for the time unit. To sum up, connected and automated vehicles have the huge potential for saving energy. Here is the outline for this talk. We have already covered the motivation, and we will present the eco-lane selection strategies and lane-changing maneuvers next. Then we present our protocol, which is named MultiCruise, and also we will present our evaluation for MultiCruise. So let's see the lane-changing maneuvers for human drivers. When we look at human drivers' behavior on highways or motorway, they adaptively and dynamically change the lane to drive in order to save their travel time or saving the fuel consumption. The lane-changing maneuvers can be classified into two different types of group, mandatory lane changing and discretionary lane changing. First, mandatory lane changing is for navigation purposes, and also discretionary lane change is for secondary purposes, such as for travel time or fuel consumption. In addition, for lane-changing maneuvers, selfish driving can compromise road safety. For example, aggressive back-to-back lane-changing maneuvers may improve travel times or energy consumption, but this selfish driving might give negative impact on the entire traffic. Overall, to develop safe and practical lane changing and lane selection strategies, eco-cruise function has to be considered, and also we have to focus on discretionary lane changing maneuver. So here is the requirements and design policy for our eco-lane selection strategies. First, road safety is primary concern, and we never compromise the safety. Target lane should have sufficient space to complete the maneuver. Also, the protocol has to avoid aggressive back-to-back lane changing maneuvers. Next, since we focus on the energy consumption, we do not consider the navigation and mandatory lane changing maneuvers. Therefore, we extend the eco-cruise component for eco-lane selection, which is named MultiCruise. In MultiCruise, each vehicle has multiple cruise targets, which drive on the current lane, right lane, and left lanes. We simply select the appropriate target vehicles to cruise for eco-driving. To design the appropriate eco-lane selection strategies, our protocol uses cost for energy and penalty for safety. We present such cost function and penalty function next. So here is the outline again. We cover the eco-lane selection strategies and the overview, and we will present our protocol, which is named MultiCruise. So let me explain the cost function and penalty for MultiCruise. First, in MultiCruise, each vehicle calculates the energy cost for right lane, current lane, and left lane by using the target vehicle's information and inter-vehicle distances by using the onboard sensors and V2X communications. In addition, to improve road safety, the protocol uses pass time T delta, which is from the last lane changing maneuvers. By considering the pass time T delta, the protocol can avoid aggressive continuous lane changings. To wrap up, by using the energy cost and penalty functions, each automated vehicle completes the lane changing maneuvers in a cooperative and energy efficient manner. Let us see the actual implementation of the MultiCruise protocol. First, To guarantee load safety, during the lane changing maneuver, we implement the space checker that is for confirming the load safety on public roads for the target lane. When the target lane has insufficient space for lane changing maneuvers, the lane changing maneuvers has to be cancelled. In addition, since the test and verification for the lane changing maneuvers on public roads might be difficult, we use the info-rich configuration platform, which is presented at IEEE Intelligent Vehicles Conference at 2020. The co-simulation platform includes 3 software: Traffic Environment Simulator, Eco-autonomous driving software, and Simulink-based vehicle simulator. We implement MultiCruise component on Behavior Planner for the Eco-autonomous driving software. Therefore, by using such Eco-autonomous driving software and co-simulation platform, we can test and verify our protocol with realistic road networks, traffic models, and vehicle models. Here is a demo video for our MultiCruise. When the vehicle finds a slow lead vehicle on the same lane, the vehicle starts to search the target lane to drive in. After confirming the safety by using the space checker function, the vehicle starts to change the lane and passing the slow vehicle. After passing the maneuver, the vehicle goes back to the original lane by using the space checker. So here is the data collected from the case study. As shown in the demo video, the vehicle has 2 lane changing maneuvers. Also, the speed limit is set as 70 miles per hour, and the lead vehicle has only 50 miles per hour. When we look at the left side figure, the vertical axis represents the yaw angle, and the horizontal axis means the pass time from the beginning of the simulations. The red line describes the value for our protocol and has 2 big changes on the value. Also, in the right side figure, we show the consumed fuel on the y-axis and the passed time on the x-axis. Compared to the simple baseline protocol, our protocol could save the fuel over 30% because of the short travel time and appropriate vehicle speed and control. In addition, to test our protocol under the realistic driving environment, we prepare the synthetic drives that are generated from the real-world driving data. More specifically, we prepare 6 different types of road networks that include highway segment, in which there are no traffic signals or other traffic controllers. Here, we show 2 different types of examples for the road networks. The left one has over 10,000 meter segments without any traffic controllers. Likewise, the right one has a very long road segment which is over 12,000 meters. In the simulation for the evaluation, we use such 6 different types of scenarios by changing the traffic volumes from 100 meters per vehicles to 50 meters per vehicles. In other words, we change the traffic density to evaluate a protocol. In the figure, the vertical axis, y-axis represents the fuel difference, which is compared to the baseline protocol. For example, in map A, under the moderate traffic, the vehicle can save around 7% fuel. Also, in map A, under the heavy traffic, the vehicle can save around 4% fuel by using our MultiCruise component. To wrap up the evaluation result, MultiCruise saves fuel consumption in all cases we considered in the evaluation. Let me wrap up the presentation and discussion. First, we present our eco-lane selection strategy, which is named MultiCruise, in which the automated vehicles keeps calculating the cruise cost for multiple target vehicles. Also, we consider the cooperative and safing mechanisms to avoid aggressive back-to-back lane changing maneuvers. Lastly, to show the feasibility of our protocol, we use the info-rich co-simulation platform and realistic road networks model, and we show the evaluation results in which the vehicle saves the fuel consumption on highway road segment. Thank you very much for your listening and your time.